This session is about hypothesis testing and what that means about in regard to research design. Nearly all research, at least research that has to do with quantitative research, is based upon some kind of hypothesis. This is a little different than qualitative research because qualitative research really is a way of developing hypotheses. So we're going to kind of stick just with the quantitative side of this for right now. Basically what we mean is we're trying to determine what is really occurring or may occur in a population, given that we only take a sample of that population. And this forms the basis of the hypothesis testing and the level of significance that we're looking for, is this difference between our sample and our population. First, we have to be very, very clear about what we mean in regard to our hypothesis. It has to be a very narrow hypothesis. And I'm going to use the example out of your book on page 15. It talks about being in a book club and whether or not that makes a difference. Their hypothesis is this, and it's actually what's called a directional hypothesis, that participation in a book club will result in an increase in the number of books read. So they had a couple of experiments that they ran. One's called outcome A, one's called outcome B. The other way they could have done that is that they could have made what's called a non-directional hypothesis. And this happens more in pilot studies, really experimental research where you're not sure what's going to happen and you leave it open-ended because you don't know what's going to happen. So for example, does participation in a book club result in a change in the number of books read by children? It's non-directional because it could go either way. Yeah, the students could read more books. Then again, if they're in a book club, they may not like it and they may end up reading less books. That's what happens with a non-directional. These are also referred to as a one-tailed hypothesis and two-tailed, and we'll see why in the next slide. If you'll remember back from your basic research, intro to research, basic statistics, thing that you've ever done with testing, anytime that you have a group of scores, you'll most likely end up with a normal distribution. In a one-tailed test, for example, the example that is given in the book, it talks about a change in the number of books read. So they want to know, is there going to be an increase in the number? If on average students who are not in a book club read 5 books, that would be here in the middle because that's the average. What they want to know is if we put some of those students in a book club, will the average go up? That's one tail, that's directional. The second type, the non-directional, means we don't know. So we have a control group that has a mean, for example 5. With a two-tail or non-directional test, it might be that the students in the book club read less books. It might be that they read more books. We don't know which way it's going to go. So that's why it's called a two-tail, because they could end up at this tail or this tail. Another way of saying a hypothesis is something that's called a null hypothesis, and you don't see this a lot anymore, mostly because it's kind of confusing. But a null hypothesis is what's behind all hypothesis statements. And what that means in relation to the book club example is two things are supposed to be equal. So on this one, the average number of books read by students participating in the book club is equal to the average number of books read by students not participating in the book club. What we want to know with our research study is, can we reject this? Can we reject this statement where that's not equal anymore? Which would also make it a two-tailed test because we're not picking a direction with this. If we reject it, the number of students won't be equal, and that's what we were wondering. So here's what they did. They have an experimental group, those who are in the book club. They have a control group, those that are not in the book club. And they're suggesting that this independent variable, this book club participation, will make a difference in a dependent variable, the number of books read. Now, I'm going to state this again. This will keep coming up. You never really know for sure because they can't put every kid in the world in the study. If they want to know if book club participation makes a difference with 5th graders, they can't put all the 5th graders in the world in the study. It wouldn't make any sense to do that. It'd be too expensive, and there's really no point in it if you do a very, very good job of sampling. If your experimental group, control group look very, very similar. If you give the experiment enough time to run, that's the purpose of doing this. So you don't have to do the sample. Excuse me, so you don't have to do the whole population. There is always a chance you can be wrong, and we know that, and we're willing to accept that. We're willing to accept that we may be wrong with our hypothesis 5 times out of 100 due to just pure luck. And that's a slim chance. And what this does is this 5 times out of 100 creates a magic number that we'll always be looking for. When you look at statistical outcomes, you're looking for something called a p-value. And you want a p-value that is less than 0.05. And what that is stating is that 5 times out of 100, less than 5 times out of 100, the results that you got are just due to pure luck. Anything that's less than 0.05 is acceptable. We're willing to say that that's okay. Now, if it is much, much less than that, that's even better. Then you can have even more confidence in your results. If it's greater than 0.05, that means there's a 6 chances out of 100, 7 chances out of 100, that the results that you see in your study are not necessarily because of what you did. They're just pure luck. That's not okay. We can't live with that. As I said, the challenge is we don't really know what is true of the population. We're taking a good guess. We don't want to make a mistake because we don't want to say something that's true that isn't. It's called a false positive statement. Or to fail to say something is true when in fact it is. It's also referred to as a false negative. To give an example of this, you have a sample. We have these people, for example, that are participating in the study about being in a book club. And as we said, this is about, for example, in this case, 5th graders. So we're trying to take a sample of 5th graders that represents all 5th graders in the country. We don't ever know what is true of the population. We're trying to do as good a job we can with our sample to represent this. And there's always going to be a relationship between this and this. And there's 4 different relationships that can happen. If, with your study, you say, yes, book club makes a difference. Kids that participate in book club read more books. And in fact, that's really is what would happen. If you really could do the whole population, that's exactly what you would see, that being in a book club makes a difference. If these 2 statements are congruent, you're good. That's what we want. If you do a study, and after the results of your study, for example, like an outcome B, you say, being in a book club didn't make that much difference. It doesn't change the number of books that the students read that much. And in fact, if we really could do the whole population, we would find that no, it doesn't make a difference. Being in a book club for all 5th graders doesn't make any difference. What you've said with your sample is what is true of the population. These are fine. It's when we get in this situation here and here. And this is very similar to the diagram that's on page 17. If you don't do a good job with your study, and you've got what I referred to in this book as gremlins in your study, and you say, yeah, I believe that, or would suggest that participation in a book club makes a difference. But in reality, if we really could do the entire population of 5th graders, we'd find that it does not make a difference. That's bad, because you said something that's true, which is not. That's called a false positive statement or a type 1 error. If you do a study and you say, no, there's not any difference at all, you get the results of outcome B. But in fact, in the population, there is a difference. It's more like what you'd see in outcome A. That's bad too. You failed to say something that's true by making a false negative statement. And this is kind of like a jury trial. Let's say, for example, that somebody's on trial for murder. Nobody knows for sure, except the guy who did it, what the truth is. So the jury, after listening to everything, convicts an innocent man. There's 2 things that have happened. They've said something that's true that's not. So two things have happened. One, they've convicted an innocent person. That's bad. But two, they've also let the guilty person go free. So that makes this a very, very bad situation. Now, the other side of that, let's say that they have the person who did it, but they failed to convict him, and they let the guilty person go. That is a bad thing to do. But they didn't convict an innocent person. They've made a type 2 error. That's bad, but it's not as bad as this, because this has two bad results. This has one bad result. I'm going to show you another video after this one about the results from the book. I've taken the data, put it into SPSS, and ran it. I'm going to show you what's happened with this significance level and what it looks like when two groups are different and what it looks like when two groups aren't, and why it's necessary to run this statistical test to really figure out what the truth is. There is no gray area with significance. It's either a difference or it's not, and you'll see this over and over. Significance is like pregnancy. There is no almost. Either it is a significant difference, either it's less than 0.05, or it's not, period. That wraps up the part about hypothesis testing, and we'll move on to the next part.